For our first talk, we're very happy to have Zoran Sunic from Hofstra University, who'll be telling us about context-free orderings on free products.
Thank you. Thank you for the invitation and introduction. Yes, the title says something about context-free orders on free products, but most of the time I will be talking about free groups, and the point is that pretty much everything I say can be extended to free products in more or less obvious way. I will mention the obvious way when the time comes, but I want to keep the talk kind of close to the ground. I'll start with ordering the free group in a very simple way. It was already mentioned in many talks, I guess. Easy way to order something is to find action on the real line, order preserving homeomorphisms and so on. But even easier is to find action on the circle and then lift it to the line. So that's exactly what we're doing here. So I'm thinking of F2, which is generated by A and B. And this is the action on the circle, where the circle, of course, we think of the circle here as a real line, small z. So this is 0, this is 1. So just divide it in 5 equal pieces, and that's the action of A on the circle, the orange thing, and the purple thing is the action of B. Here, capital A and capital B will be the inverses. So capital A is the A inverse, capital B is B inverse. Okay, so this is the action of B inverse and A inverse. It's an obvious, more or less, argument, ping pong argument, that these two homeomorphisms of the circle generate a free group. What you need to observe is the following. Well, let me write it here. Whenever I apply A to any region in the circle except this one, any region except R capital A, well, whenever I apply such a homomorphism, I land in the region RA. Whenever I apply B to any region except the region capital B, so whenever I apply the purple thing to anything except this region, I will land in region B. And similar thing down here, if I apply A inverse to anything except the region that is reserved for little a, I'll end up in the region that is reserved for capital A. So anything but this region is mapped to RA, capital, and B inverse. Again, this is completely trivial application of ping pong lemma. So obviously then, by ping pong, I have this, that these two homeomorphisms actually generate free group. Moreover, these regions are telling me exactly where I land after I'm applying any of my generators. So, by the way, my action is on the left. So when I write A, B, C, it means C, well, there's no C, but in general, C is applied first, then B, then A. Okay, that's a left action. In other words, the first letter in the word tells me where I land. So if I apply something like this, A, B, whatever, A, B, to say 0, and I keep track where I'm landing. Well, I don't know exactly where I land, but I'm sure I will land in the region little a. So that letter tells me where I land at the end. Okay. Well, once you have action on the circle, you promote it, you lift it to the real line in obvious way. So it commutes with the map x goes to x plus 1. So there it is. Okay, and the good news is not only this is action of the free group, but the orbit of 0 is free. You never go back to 0. Once you apply anything at 0, you will land in one of these 4 regions, and you will never go back to this region that has no label whatsoever. Okay, So you have free action on 0, and therefore by all sort of folklore reasons, you know that you can now define order on the free group. Namely, you can say G is bigger than identity, if and only, so we just define this order, if and only if G moves 0 to the right. That's positive. Okay, so we have an order. Now, since these maps are very concrete, this A and B, you can actually calculate G of 0. This is piecewise linear with slopes 1/4 and 4, blah, blah, blah. You can write formulas, but you don't really need to know the value of G of 0. You just need to know whether it's positive or negative. So let me write some strange looking formula, but in a minute it will be obvious that it works and why it works. So I'll define tau function from the free group to, well, 1/2 z, by which I mean integers and half integers. And the map is defined as follows. Tau of G is the number of occurrences of the subword BA in G minus the number of occurrences of capital BA in G. And then there's this additional part, 1/2 if G ends A or B, a little A or B, and negative 1/2 if it ends in capital A or B. All right. So that's just a formula. By the way, this formula is only should be applied when G is reduced. Otherwise, it's nonsense. Okay. Otherwise, it's not well defined. So G reduced. So if you want to calculate the value for some element, reduce it first and then start counting. All right. So I claim now that the following is true. So the value of this element, it will always be something like n plus 1/2, or yeah, it will always be plus 1/2. This is integer, and eventually I'll have plus or minus 2. I mean, plus or minus 1/2. So the value will always look like this. But the claim that I'm trying to make is that this happens if and only if G of 0 belongs to the interval n plus 1. Why is this? Well, like I said, I don't want to keep track exactly what G of 0 is. I just want to keep track in which interval I land. If I land in a positive interval, I'm positive. If I land in a negative interval, I'm negative. So what happens at the first instance? I'm here and I apply, say, either little a or little b. That's my last letter. So that will give me value 1/2 or negative 1/2. Well, if I apply first little a or little b, it gives me value 1/2. 1/2 is right there, and that's exactly in the interval from 0 to 1. Okay, and similarly, if I apply, I shouldn't look here. I should look here. If I apply A inverse, I will land in the interval here. So again, the formula says negative 1/2, but I'm landing into interval negative 1/2. I mean, negative 1, 0. That's where I land. When I apply capital A to 0, I'm landing here. Or capital B, I'll land there. Okay, so that's the last letter. So this takes care of the last letter, basically. And just tells me, oh, you moved slightly to the right or slightly to the left. That's all it says. And after that, this part is actually much even easier to understand. This just counts how many times I jump over an integer. That's all it does. How can I jump over an integer to the right? Well, the only way to jump from this interval, whatever it is, from n to n plus 1, say, to jump to the next interval, well, I cannot do it from here because I cannot apply A to a region that is capital A. You only land here if you ended with A inverse or started with A inverse. Therefore, it wouldn't be reduced word if I apply A. So it's impossible to reach the next guy from there. How about from here? Well, if I apply, well, again, from here, I cannot reach the next one for the same reason. I cannot apply B to the region that is reserved for B inverse. So the only way to advance is if I was here and then I apply little b. That's the only way to move to the next box, basically. Well, being here means the previous word was starting with A, and then I'm applying B. Well, that's appearance of the subword BA, which is that one. And same story if you go down. How can I go down? The only way to go down is to be in the region A and apply B inverse. And that's it. I just keep track how many times I jumped over an integer to the left or to the right. So that's the job. So in other words, now we have little proposition, if you will. I know now that G of 0 is positive. Well, if and only if tau of G is positive, and therefore I have a very easy criterion to decide whether my element is positive or not. All I have to do is go through the word, count VAs, like VA inverse and V inverse A, and do this 1/2 at the end, just to make sure I don't get 0. And that's it. So you have a very, very simple description of an order on the free group. Now, I'll say a couple of more words about this order. And pretty much, well, almost all of them obvious. So let's see. One thing that I can say is this order, so the order that we defined, this order, extends the lexicographic order on the positive words, so on A, B star. So if I only look at the positive words, words in little a and little b, the order that is induced on those guys is just the usual lexicographic order in which A is considered smaller than B. And you don't have to do any calculations actually to see that. It's obvious for dynamical reasons. Look what is happening. When you apply A or B to anything, okay, I start at 0. I apply, I don't know, A, then maybe A again, maybe B, maybe A. I'm trapped in this little region. I will never leave this region, first of all. Okay, so starting from 0, keep applying little a and little b, well, you will never leave that little region. And whenever your word starts with A, you will end in this region. Whenever your word starts with B, you will end in this region. But that means the word with A is smaller than the word with B because I'm further to the left. So anything that starts with A is smaller than anything that starts with B, as far as positive words are concerned. You also have to prove that, positive, another thing that you have to prove is that anything that is a positive word is actually positive. Because, okay, you have to prove something like, okay, B is smaller than ABB. You need to know that. Actually, no. You want to know that things like this are true. Of course, this is true if and only if this is true. But that is true. Any positive word will actually move either here or here, so I'm positive, so I'm fine. Okay. So that's really obvious exercise, and you don't even have to use the tau for this. You could use tau and see and evaluate, and you will see. But you can see it in the picture. Another thing that you can see in the picture is the order is, to remind you, order is discrete if every element has successor and predecessor. Or to say it differently, there exists the smallest positive element. The smallest positive element is A. And again, it's obvious from here. what happens when you apply A to 0? Well, A applied to 0 is, I guess, 1/4. No, 1/5. You end up right there. Nobody can move further to the left from that point and stay positive. And remember, the action is free, so that's the only guy that can get there. There's no another element that can land in the same place. That's it. So you have discrete order. The next one is just for fun. This one is closed under reversal. Under word reversal, let me say. If any word is positive, flip it around, stays positive. I don't know other orders like that on the free group. I mean, I know now uncountably many orders like that. At some point, I didn't know any also like that. Okay, and the last one is this is so-called well, the one counter language. So the positive cone, the positive cone can be represented by a one counter language. You don't need to know much about languages or anything. Here's the picture in which I actually represented precisely the positive cone of the free group with respect to this order, except I didn't finish the picture, but we'll finish it right now. So this is B. This is -2, and this is plus. Okay, let me explain the meaning of all this. So, as you know, okay, languages are studied by kind of you create some formal machines that process the word in some way, and then eventually they should either accept or reject the word. So this machine, whatever it is, will only accept the words over this alphabet A, B, A inverse, B inverse, that represent positive elements in this order. And how does it work? Well, first of all, the machine pretty much evaluates tau in some sense, except I don't like the halves now. Just multiply by 2. Make the weight twice as before. So let's just say T prime of G is twice tau of G. That will make my map going from F2 to Z. Previously, I wanted this so that I have actual geometric meaning what what tau of G is. It's in the middle of the interval where I land. But now, for convenience, I'll just make the values integer. So double everything. Okay, and now it's clear what is going on. If my word ends with A, I'll read words in the wrong way, from right to left, because that's how they act, remember? So this is the first guy that acts. If the first word is, first letter is A, the first one that acts, so the first one on the right, I add 1 in some counter, in some B, okay? And then I continue reading my word. Next letter is B, I land here. Next letter is A inverse, I land here, and so on. And whenever I pass along this edge, that means I was in the state A, I was basically in the region RA, and I applied B. Oh, that means I should add to my counter, but I'm adding 2 now. So I add 2 more B's in the file. And so on. Whenever I pass through this edge, that means I was in the state that corresponds to A, but I applied B inverse, but that's exactly the thing that I should count as -2. And that's what I'm doing. So just follow the word and put B's on the pile or take them off. And you only have to do it here and here. At the end of the story, once you finish reading the word, all you have to decide is, do you have negative number of B's in your counter or positive number? From what? Oh, yeah, sure. I didn't finish the picture, but yeah, thanks. And that one is one of those that is irrelevant, doesn't contribute anything. Thanks. Okay, so this is so-called push-down automaton, but very simple push-down automaton that uses only kind of single counter. The alphabet of the stack for the experts consists of only one symbol. It's not complicated alphabet. And again, quickly, there's this hierarchy of languages. It's much more involved, but I'll just put the basic picture. There's regular languages, there's context-free, then even more complicated languages, context-sensitive, and let's say the last one, recursive or Turing recursive. Okay. So anything that we can calculate. All right, so this is the simplest one. And that's the next interesting class, the context-free. If you can recognize something by using this type of machine that has a very simple memory, like here, that's context-free. Moreover, like I said, the one we just did is so-called one counter, which is almost as close to a regular as you can wish, but without being regular. Because I do need this memory, this stack where I put this B. Okay, so that's that. So we have one order so far, but very quickly we'll get many. Yeah, so in a sense, this order, the one that we were looking at so far, is associated to this word A, B, B, A. So this is the order A, B, capital B, A. This is precisely the order of the regions. And here I had a picture for a different one. Here's a different action of the free group, where I just ordered my regions differently. And that's pretty much the only difference. I can now repeat this entire exercise. It's a little bit more complicated. What will be the corresponding weight function? So you can think of this as a weight function that tells you if something is positive or negative. So again, you can keep track how many times you jump over integer to the right or to the left, and you can write a formula that looks, well, a lot like the previous one, slightly more involved perhaps, but so for that other picture, for the word A, capital A, little b, capital B. So for that order, the weight function is tau of G is, well, let me do the double one. So the values are integers. Twice the number of appearances of little ab minus twice the number of appearances of little a capital B, no, plus. And then minus twice number of appearances of capital B little a minus twice the number of appearances of capital B capital A, and plus this 1 or minus 1, depending on the last letter. So last letter AB, last letter AB. Okay, so that one will give you order that corresponds to this action.
Excuse me.
Yes.
Is the your map doesn't quite seem to it seems to have a chunk in it. For B, is it supposed to? It doesn't match up on the top and bottom.
How come? Oh.
Okay.
Thank you. You're right. Should be here. Yeah. Sorry. That's what I meant. Yeah. Okay. So now I have at least two different orders. You can verify that these orders are different. But what I'm saying now, you can build uncountably many because I have 24 orders. For every permutation of these four regions, I can make an order. Okay. And each of those orders will be this kind of context-free. I can. Yeah.
You mind just saying out loud again how you got this outline? You said it.
This one.
Just the whole where you got the four.
Yeah, this whole thing. Okay. You followed how I got this one? Well, I'm doing the same thing. Start with this action on the circle, lift it to the action of R, and then start counting under what circumstances you're jumping to the right over an integer. For example, yeah, let's do example. If I really kind of extend this, it will start looking something like that when I lift it. So, for example, if I'm in the region D, little b, and I apply A, I will jump over an integer. So AB should be counted as +1. And that's right there. Except I multiply by 2 to get the integer value. So that's that, for instance. So you just do this little analysis, who is pushing you over integer to the right, who is pushing you over integer to the left. And that one just takes care of the very first step. Did you make the first step to the right or to the left? Now I'm saying you can now build uncountably many orders by simply saying, well, on the interval from 0 to 1, behave like, I don't know, like this guy. On the next interval, once you kind of give control to the next interval, behave like any other of these guys. Or in terms of these little machines, when I was supposed to add +2, I will add +2, but I will not connect to this b. I will connect to the little b in the next machine, the machine that corresponds to this other word, because this is the machine that only works for whatever this one was, A, B, D, A. This is the little machine for that. Okay, so I can string along many of these little automata and make infinite automaton to the right and to the left. But it still does the job. It calculates who is positive, who is negative. Moreover, if I do it in such a way that I'm eventually periodic, if this the choices that I make here are eventually periodic in both directions, that whole thing will still be just a finite automaton. I can use the periodicity and I'm fine. Okay. Moreover, obviously, this class of context-free languages or orders that is inside this uncountable class of orders will be dense inside, because when two of these agree for a very long time around 0, they will agree on short words. When I apply G to 0, if I have the exact same little machines in every interval for a while, remember my G never jumps more than 1. So for a very long word, I will do the exact same thing. So again, agreement in this choices of permutations. I have 24 letters, basically. If you want to talk symbolic dynamics, I have 24 letters. I'm just making it by infinite words. As long as two by infinite words agree for a long time around 0, the orders that they find will agree. So in this space of orders, they will be very close to each other. Okay. And then what I'm saying is, of course, if you do it in eventually periodic way in both directions, I'm actually getting context-free order defined by context-free language, and that thing is obviously dense inside. Okay, what else? Now, if I want to create only, say, extensions of the lexicographic order, so yeah, maybe I should start erasing stuff. Yeah, this is not this. For extensions of lex, use only A, B, BA, the one that we started with, and A, B, just use these two and alternate them any way you want. So you will create again uncountable family of orders in which each of them will be extension of the lexicographic order. And inside, I have a dense subset of context-free orders. For discrete orders, use only, well, that one, we already know it's good. And this is another that will be a good friend. So yeah, just use these two. Here, the important thing is that all my little letters are before all my large letters. If I want to do this on on F3, I will use only things like this, where the regions are all small letters are before all the large letters. That will extend lexicographic order. If I want discrete orders, the first letter should be inverse of the last letter. That will give me discrete orders where this guy is the smallest. For extensions of short-lex, short-lex is in many applications more convenient than lex because at least it's two-sided. Short-lex is two-sided order. But nevertheless, extensions of short-lex use only, well, here it's kind of the other way around. All the big letters should precede the small ones. And then every order that you create, this uncountably many orders there, will be extension of the usual short-lex on the pre-monoid. Shorter positive words will be smaller. Yes?
What does short-lex mean?
Yes. For the positive monoid, short-lex means shorter words are always smaller than the long words. And then if they have the same length, you compare them lexicographically. So length first, then lexicographic. It's much more convenient in many kind of algorithmic applications, basically. Because you always know who is next, for example, here. Yeah, that's a very good thing about this order. There's always next guy in the list. Okay.
No, these orders are less invariant,
Yes, absolutely.
but we know the free groups have two-sided invariant ordering. Is there a way to do that?
Not with this technique. This technique basically finds only one-sided. In particular, for instance, lexicographic order is decidedly one-sided. So you cannot extend it into a bi-order, no chance. Short-lex is two-sided, but these extensions are one-sided.
For like short-lex, at least A inverse counted as -1 or 1.
Excuse me?
The length of like A inverse in short-lex is counted as 1 or -1.
Again, we are only ordering by short-lex the positive monoid. So I'm only looking at the positive monoid. And all I'm saying is these orders that I'm building just extend that order. So on the positive part behaves like short-lex. Everything else is, well, behaves in many, many different ways depending on what choices you make here. Yes.
For these discrete orders, which is the smallest positive element?
A. When I do it with these two words, A is always the smallest positive element. Just like it was here. You'll pretty much get this kind of picture. Okay. All right. So now let's go back. Okay, I need to say some things are also happening for free products. Well, it's slightly less obvious that I can do this for free products. And I can definitely not do it by showing you nice actions, because who knows, I have two groups, A and B, okay? And both of them are orderable, but I don't know good actions of A and B. So I cannot even tell you how A and B act, let alone to put them together and give you action of the free products. So I have no chance of doing that. But the nice thing is, well, yeah, I lose some of that geometry, but I don't lose the insight that I can do things by these kind of things. I can measure the weight of stuff. So here's a theorem. Well, let me. Okay, so how to order A star B. Again, I can do this for arbitrary free products. So of course we assume that both of these are left orderable, and then we start from there. And I'll write the formula now. For arbitrary element, I'll define the weight. And the weight will be, let me write it and then I'll explain. Number of positive syllables minus number of negative syllables plus number of A plus minus to B plus minus transitions, and minus number of B plus minus to A plus minus transitions. I'll explain all this. Let me just record the formula. There's a formula. This is obviously a function from from G, from this free product to Z. And I claim that this okay, what are syllables? Well, it's free product. So if you're not familiar with free product, it's fine. Just think of free group on A and B. Yeah, just think free group on A and B. I should start erasing stuff. Okay. Actually, I don't like this one. Okay, I don't think I need that anymore. Okay, so again, free group. What is today? 4th of May. A to the 4th, B to the 5th. Let's say capital A 2023. What's B to 1 billion? Okay. So the point is, again, I don't care how large these things are, because as you saw already, one reading through the word is telling me something is positive or negative. So my formula now says count the positive syllables. That's a syllable, like power of A. That's +1. That's a negative syllable. That's a positive syllable. +1. Negative syllable. So it doesn't matter that the 2023 of them, it just counts as -1. And this one counts as +1. So those are the 4 syllables here. If you're in free product, of course, you're just counting there's element in A, non-trivial element in A, followed by non-trivial element in B, non-trivial element in A. And because both A and B were ordered, some of those syllables will be positive, some will be negative. So you can always do this calculation. Moreover, I need to count transitions. This transition is from A to B. It counts as +1. This transition is from B to A. It counts as -1. And this one is from A to B. Counts as +1. And then just add the numbers and it will tell you whether this thing is positive or negative. So 1, 2, 3, 4, 5, -2, 3. So this element is positive. Now, I will not prove that this works. Some of you have seen this probably more than once. I want to show you the new thing. So when you do it this way, this is not discrete or anything. So A is not convex in B. Yeah, if you do it this way, A is not convex in B. Again, what does that mean? Well, it's probably easier to explain what convex means. Let's say A is, let's say, subgroup of some left orderable thing. A is convex in G if, well, for every G in G and for every A in A plus, so every positive element in A, if G is between 0 identity and A, that implies G is in A. All positive elements of A are smaller than all other positive elements. That's a way to say it. Or you have identity here, and then around it is the subgroup A, and then this way is the rest of the positive guys, and this way are the rest of the negative guys. So A is convex. All right, so if you look at this order, A is not convex in the free product. So I want to show you a way to do it in a way that will make A convex. Well, let's just fix this wordings. Well, this one is now different. So this one is pretty much the new thing. The number of positive chunks minus the number of negative chunks, and then some transitions are counted. Number of Well, let's put it this way. The positive. BA and AB transitions and negative AB BA transitions. Okay, so now I need to explain the meaning of these things. What are these chunks that I'm talking about? Well, if I go back to this word, let's write it again. A to the fourth, B to the fifth, capital A to the 2023, and little b to the power 1 billion. Well, chunk is something like this. This is a positive chunk. It's a positive syllable followed by positive syllable followed by positive syllable. So as long as my syllables are positive, I just put them in a single chunk. Okay, so that's a positive chunk. So basically, I'm only interested in the sign changes when I'm switching from positive to negative, or the other way around. Before, every time I switched between letters, I was kind of paying attention. I was counting positive syllables, negative syllables, and all possible transitions between letters. Now I don't really care that much about letters. I'm kind of concentrated on the sign changes. So that's a positive chunk. Maybe I should add at least one more. A, and then maybe B squared A cubed. Okay, so there's a positive chunk. Here's a negative chunk. Okay, negative chunk. Well, negative. So this one will be counted as +1, this as -1. This one will be positive chunk, +1, negative chunk, -1. And then transitions. Well, BA, this kind of transition from this basically it's easy. Transitions that involve positive element from B and negative element from A. That's the point here. So positive element from B and negative element from A, that's counted as +1. Transition here also involves positive element from B and negative from A. So that's also +1, and here it's a -1. This is a transition that involves positive from A and negative from B. So that's mine. And I'll just add it up and see what we get. 1, 2, 3, 4. I got confused. But I was counting. 1, 2, 3, 4, 3, 2, 1. Okay, positive. This thing is positive. And here, if you do it this way, A will be convex in B. Okay. Now I have 2 minutes or 12 minutes. 12.
1 second.
Well, I'm thinking what to. Okay, let me not prove anything of this type. The proofs are really elementary. Okay, let me just quickly say a few words. How do you prove that this is even an order? First thing to observe, the number that I'm getting is always odd. When I calculated in the previous case, I got 3, now I got 1. So I'm claiming this thing will always give you an odd number, which is great, because it never gives me 0. That way I can decide who is positive, who is negative. Why the number is always odd? Well, let me go here. I was counting some number. Oh, I will look at this number mod 2. Mod 2 means I can make them all pluses. Number of positive chunks plus number of negative chunks. That's just the number of all chunks. Number of chunks, sign changes that involve positive element from B, plus number of sign changes that involve positive element from A. That's all sign changes. So here I have 4 chunks plus 3 sign changes, that's 7. So that number is 7 mod 2. And it will always be odd number. No matter how many chunks you have exactly that many -1 transitions between signs. So the number is always odd. So tau G is different from 0. That's all we really care, as long as G is not 0. So that's one thing. Second thing, tau of G inverse is negative of tau of G. And that's also obvious. When I invert all positive chunks become negative chunks, and vice versa. All transitions of this type become transitions of this type, and vice versa. So everything just flipped. Now these two together are already the trichotomy. This says everybody except 0 is either positive or negative. And the inverse of G, and well, this is saying basically you have the positive guys, disjoint union with the negative guys, disjoint union with the identity. That's trichotomy. The only thing that is left to prove is that product of positive things is positive. But that one is pretty much trivial as well. You just have to look at several cases. The thing is, whenever, let me just write the important thing. You can prove that for any two elements, the tau of Fg and the tau of F minus tau of G, this number is either plus or minus 1. So whenever you take a product of two elements and you evaluate tau, it differs from the sum of the taus for those two elements by exactly 1. Again, it's just several cases, you know, when you take one of these guys and you multiply it by another of those guys, what changes in the middle? There's some new transition. But you consider all cases and you see that whenever you kind of add some -1 because of something, some positive one is also added, so nothing really changes. And therefore, since you know that things never change by more than 1, if you take two positive things, this one has tau at least 1, the other one has tau at least 1, and when you multiply them, the total tau can only change by 1. So 1 plus 1 minus 1 is still 1, so I'm still positive. Okay, so it's fairly elementary to actually verify this. Just look through several cases. Okay, and now in the remaining 8 minutes or so, let me go back to this regularity question. I showed you many context-free orders on the free group. Well, can you do something better than that? And the answer is no. So here's the theorem. Kermiller says no order on free group can be represented by a regular language. This kind of question was asked by now a long time ago. Caligari proved that for hyperbolic three manifolds, the positive cone cannot be described by a regular language that consists of quasi-geodesics, for example. But that's a very old result from 2003. And he asked, what is the complexity of orders that you can put on the free group? Well, now we know we can put one context, one counter language, very simple, very close to regular. But we claim here that you cannot do it by a regular language. So pretty much this is it. And again, for those that don't know what regular language is, let me just give you an example. If you look at Z square with the obvious lexicographic order, where positive things are, you said green is not that. Okay, these are the positive things. Either you are positive in the first coordinate, so everything that is here is positive. And if the first coordinate is 0, then you look at the second coordinate and that's considered positive. So this green region is the positive stuff. You can represent this positive cone, this thing to the right of this green line, by a regular language or by automaton, if you will. You start here. If you read A is this direction, and B is this direction. You read A, and then you are free to read as many A's as you wish. So you're traveling along this. And then you're free to read B, and you are free to read as many B's as you wish. Or if you are here, you can also read B inverse if you want. And after that, you can read as many B inverses as you wish. And there's another option when you start from here. Okay, that's your start. You can read B and as many B's as you wish after that. And that's it. So we will kind of, how do we recognize or accept what? Anything that I can read in this graph, starting from here and ending in any of these other four states, is a good word, is a positive word. And they're all covered. And unlike in my case before, when I needed to put some counters on the side on a pile, here I have practically, well, zero memory. Okay, I have a little bit of memory, that is the states themselves remember something for me, but I don't have external thing. This is a finite, predefined amount of memory that I need. That's a regular language. Anything that you can recognize by using this finite graph with no external memory that is unbound. Like for the one counter thing, I had to have this stack where I will put my little beans. And that should be unbounded in theory because I have no idea how long the word will be. So in theory, I have need for unbounded amount of memory. Here, I have absolutely no need for it. It's all finite. Okay? So that could be regular. And you cannot do this thing on a free group. You can do it on many, many interesting groups, as there's lots of very nice results by Antolin, Cristobal Rivas, the student of Iago, Sue, also Alonso and Boom. They proved in many instances that something cannot be regular, and in many instances that something can be regular. Particularly fascinating is the following. F2 cross Z. This one. So I told you F2 does not admit any regular order. That's this theorem. This one does. There is an order on this group that can be recognized by a finite machine, no need for memory. It sounds strange, but it's not. It's a very, very nice idea. You see, this copy of Z. What? No, this is the work of Sue, and then, like I said, Rivas, Cristobal, Iago, extended together with Sue this to many other classes. But again, let's keep it elementary. This one does not accept regular representation of the positive cone. This one does. How is that even possible? Well, they use very cleverly this copy of Z as the counter. After all, I needed a counter to recognize the order on F2. So they just use this guy. It's right there. There's this third generator. So I have A, B, and there's this third guy. This third guy is kind of placed in such a way that it really counts, whatever is supposed to be counted. And it works like a charm. And more generally, they prove that whenever you can recognize, obviously, whenever you can recognize something by one counter, then this thing can be recognized by a regular language. So groups like this are simpler than groups like this. Okay, so let me stop here.
Questions for Zoran?
How about the three groups with not greater than two? I mean, the three group of 3 or 4 or
Yeah,
similar construction, right?
absolutely. Everything is the same. Like take any permutation of the 3 letters and the inverses, make the regions like this, and then you can create the action. By the way, I don't even have to draw the picture. I can read. If you give me the word, I can immediately tell you the formula for tau. There's a direct way. You don't even have to draw the pictures. So just give me any word that contains every letter in the inverse once, and I can write tau for you, the weight function. Everything works. Yeah, you can even use it to order the group of infinite rank. There's absolutely no problem. Because, well, the group of infinite rank is just a bunch of groups of finite ranks, bigger and bigger and bigger, so you can do it. And the construction with Warren Dix works for arbitrary free products, even uncountable ones. By the way, yeah, that thing works for, remember, you cannot do action on the line when things are uncountable. But that weight function works. Doesn't care whether things are uncountable or not. So when A and B are uncountable for the free product, or the indexing set is uncountable or whatever, you have no chance of action in the R. The weight function doesn't care. Just calculate. I have, I have, of course, I conjecture that the bi-orders cannot be represented by a context-free language. So it's kind of next level of difficulty. I have some preliminary results, but nothing to brag about.
You talked about this kind of discrete orders, which the A is a smaller positive element.
Yeah.
Do you know something about another order like that, but with a smallest positive element, it is another element, like for example the commutator? Or
well, in theory, there is such a thing. With results with Iago and Dix, we have these results that in the free group, if you take some kind of a maximal cyclic subgroup, that thing can be made to be smallest element. You can create discrete order based on that element. In particular, the commutator can be the smallest element in an order of a free group. Except I have no idea how to write a weight function for that. The proof is Zoran lemma.
I was asking because more like a context-free option like that.
Aha, well, yeah.
Okay.
But in any case, I don't know how to do it for the commutator. I know how to do it for the generators or for any three-factor basic. Yeah, before with Dix and Iago, we had this theorem that every three-factor is can be made convex, but also was relying on Zoran lemma basically. But now it's kind of easy. You can do it. You can do it at home. Yeah.
I would like to ask how to prove the capacity of A. I mean, you experiment.
Well, it's very simple. All you have to prove is the following: if G is positive, so if tau of G is positive, this should imply that tau of A inverse G is positive. And it's very easy analysis. Each time you kind of put an extra letter A inverse to the left, how did tau change? There was one extra transition maybe and one extra negative plus. It's a trivial calculation. I don't know how to do complicated things, only simple stuff.
Okay, so maybe all the other questions can be asked during the break. Why don't we have some coffee now? We'll reconvene at 11.